Good afternoon, everyone. My name is Aditya Sharma, and this is Advanced Thermodynamics and Combustion course being conducted under NPTEL, right? And this is the third live tutorial session in the series of 13 such live tutorials sessions. And the theme of this week's uh, lectures uh, is entropy and exergy. Uh, right, and in the previous session, we focused basically on entropy. And in this week's lectures, the focus has been on exergy, right? And as we all know, the instructor for this course is Professor Niranjan Sahu from Department of Mechanical Engineering, IIT Guwahati, and I'm the teaching assistant for this particular course. Right. So we shall wait for another 5 minutes, and after that we shall start today's session. Thank you. Okay, so I believe we can start, or we should start today's session. So, as I have already mentioned, the focus of today's session will be on Exergy, as the lectures have focused on Exergy in this particular week, right? So, and the session has been divided into three sections. First section is the topics that have been covered in this week's lectures, and briefly we should discuss that. And then we take conceptual questions in the next section, and in the last section of this session, we shall see the numerical questions, right? As we have been doing in the previous sessions also. So, so to start with, we started this week with lecture 7. So total 3 lectures are there in this week's lecture, right? So we started with the isentropic process. So in previous lectures also we have been introduced to isentropic process. What an isentropic process is. Literally it means when the entropy remains same, right? So using this concept, we move on to the isentropic efficiency for different devices, right? So in our power plant, right? Or maybe in engines, right? Axial flow engines, right? That are used in aircrafts, right? So these devices, so if we have to find the efficiency of these devices, so in that case, we compare the actual case with the isentropic case, because the isentropic case is the ideal one, right? So in that case, I'll just draw the diagrams for turbine and compressor, right? So in this topic, we saw the efficiencies of turbines, nozzles, and compressors. So I'll just draw a few figures, right, and also write the formula for these efficiencies, right? So isentropic efficiencies. Anywhere you feel that you have some doubt, you can just let me know, right? So for turbines, first I'll just draw a quick diagram, right? So this is a HS diagram, right? Which is also known as Mollier's diagram. We have studied this in previous session. So let's say this turbine is moving from this to this state. So the straight line from 1 to 2s signifies that it is isentropic, right? There is no entropy change. But then actual change is actual uh, expansion path, right? Because expansion takes place in turbines is 1 to 2, right? In that case, the efficiency we write is something like this. So had the turbine chosen isentropic path, so this would have been the enthalpy change, right? But in actual, we get this, right? So it can be, sorry. You can show it here also. Just see this and you see this. Right? So this is H1 minus H2, right? And this one is H1 minus H2 plus. Right? So this is for turbines. Similarly, for compressors or pumps, right? So the diagram is this way. Right. Again, it's this diagram. So in this case, it is moving from here to here, right? And now, if we wish to see, right? Yes. So this is H2 minus H1, and this is sorry S2 S minus, and this is S2 minus H1. In this case, we write NC as H2S minus H1, which essentially means that if we have to do some work to compress some gas, maybe in some system, in that case, we will require more enthalpy, right? In comparison to the isentropic process, right? So if we do it isentropically, in that case, the in terms of enthalpy, the requirement will be less, right? But it will be greater for the actual case, which is this one. This is the actual, and this is the isentropic. Then for nozzles, we saw efficiency is written as, so the V2 here is the exit velocity, right? So in this case, what will be the exit velocity when the conditions are isentropic and when the conditions are actual? In this way, this efficiency we calculate for nozzles, right? Then moving on to the next topic, which is work transfer in a polytropic process, right? So here, first of all, we'll write the equation of state for polytropic process, right? Where P is the pressure, V is the volume, and C is constant, right? Right. So in this case, we saw uh, formula for work, right? And we saw for a journal formula, and then we saw a special formula for this ideal gas, right? So I'll just write down for maybe this journal formula. I'll just write down. Okay. So this is okay. So this is basically when n is not equal to 1, right? And then when n is equals to 1, in that case it becomes, this is when n is equals to 1. So this way there is a, formula for ideal gases also, right? So this discussion has been done in this particular topic, in this lecture. Right? And then we move on to the next lecture. Right. So in the previous lecture, in lecture 7, we saw isentropic efficiencies of turbines, compressors, nozzles, right? And then we saw the formula for polytropic process, right? And then special case also we saw for ideal gases, right? Where using the its equation of state we derive the work, right? Work transfer rate. Then, so in lecture 8, now here the concept of exergy has been introduced. So what is Exergy basically? So various statements have been passed in lecture 8 regarding the Exergy, right? So for example, Exergy quantifies the potential for use of energy, right? So what is the potential of the energy in a system that can be used to get work from that system? So this is Exergy, right? According to one statement. And then another statement says that this is maximum theoretical value of work from a system, right? So the maximum theoretical value of work that you can get from a system, uh, taking into consideration also the exergy destruction, right? uh, that we saw in the previous session in terms of entropy production, right? Which is the result of internal irreversibilities in the system, right? So this is mm, exergy, right? So then various uh, aspects related to exergy have been discussed, right? Like exergy cannot be negative, right? And then exergy is uh, not conserved, right? So like energy is conserved, that is not the case with the exergy, that exergy is conserved. Later we will see why, because the uh, irreversibility has also been included in the exergy term in terms of entropy production, and then which boils down to exergy destruction in the exergy statement, right? And then we saw terminologies, right? Terminologies when we are discussing exergy, terminologies like system, then environment, then dead state, right? So system is our system, right? And then the system, when it changes its state, initially it has some potential, right, to do work. Then it uses that potential to do work, and it comes into equilibrium with its surrounding, right? So the surrounding here has been called the environment, right? Second, so this is the second term in exergy discussion. So first is system, then is environment, then is dead state, right? So what is dead state? Dead state is the final equilibrium state in which your system reaches after it has expended its potential to do work, right? So this is dead state, right? So I'll just write down terms. This is system, then there is environment, then there is dead state. So this is about terminologies. Then we moved on to exergy of a system, right? So exergy, as I've told, it's basically the statement for work is exergy, right? But then what is the maximum theoretical work that we can attain from a system? That we call exergy, right? So we denote exergy as, so I'm discussing exergy of a system. So we denote it with capital E, right? And then uh, for a system, its statement is as follows, right? So if a system is in some particular state, right? In that case, what will be its exergy is defined by this particular formula, right? In this case, U is for internal energy, right? P is for pressure, V is for volume, T is for temperature, S is for entropy, and then there is kinetic energy and potential energy, right? So when I'm writing here naught with some terms, right? Like U naught, V naught, S naught. So these correspond to the dead state, right? That I have just written here, right? The equilibrium state that system eventually attains after expanding its potential or exergy, right? So this is exergy of a system, right? Then, then in this lecture, the last topic is closed system exergy balance, right? So in this week or in this topic of exergy, two balances we have done, right? So one corresponds to closed system, and then second one corresponds to a control volume. So control volume in which there is some flow, we have some control volume, and there is a flow in that control volume, right? And then we try to balance the exergy in that case, right? So I'll just write the balance for closed system, right? Okay. So for two states where our system is moving from state 1 to state 2, in that case, if we have to find out the exergy change, so we do it this way. TB is for boundary, right? Temperature for boundary. So if there is exchange of heat across the boundary of system and surrounding, in that case, the temperature in that scenario, right? Okay. This and then minus PU. So I was discussing earlier that in the previous session we discussed the entropy production, right? And here it comes in the exergy balance term as exergy destruction, right? So when we talk about exergy change, right? So this exergy change comes from two terms, right? One is this, which is exergy transfer, right? Across the boundary, right? Because it's a closed system. In that case, heat terms, right, can come into picture for Exergy transfer, right? And then there is this destruction, Exergy destruction term, right, is there for the closed system Exergy values, right? So Exergy basically is, please always remember that Exergy is nothing new but just the work, but the maximum theoretical work. Okay. Right. And then for steady state conditions, this Exergy change is zero, right? So obviously the term steady state means things are steady. In that case, the Exergy change is zero. Right. Right. So this is about lecture 8. Then, then is the last lecture of this week, and here we discuss the Exergy rate balance for closed for control volume, right? So Exergy of closed system we discussed in the previous lecture. Here is Exergy rate balance for control volume, right? So in case we have some control volume and we are studying some flow, right? In that case, how do we define the Exergy rate balance, right? This. So I'll just write down. So we please remember we have done the entropy balance also in the previous session, right? So this is somewhat similar to that topic, but here we are dealing with Exergy. There we were dealing with entropy, right? Some, so if you compare the two topics, you can obviously surely find some similarities, right? So I'll just write down the mathematical statement or formula. This, and then there is another term. So, so, so what is the new term in this uh, balance? If we compare with the above balance, if you see, right? So above one we have not done in terms of rate, right? But here because we have a flow, so we are doing it in terms of we have uh, brought the time this element also into this topic, right? So this, if you see this term, this corresponds to the heat transfer, right? For the system and surrounding, right? This corresponds to the work transfer, right? And this corresponds to the Exergy destruction, right? Because of irreversibilities, right? Then this is something new, right? In this balance. So where it comes from? So basically, when we are discussing a control volume, right? So here we are discussing a control volume, In that case, there will be entry of some mass in the control volume, and then there will be exit of mass from the across the control volume, right? So we have discussed the same scenario in the entropy balance also for control volume, right? There also such terms were introduced in that balance because of this mass entry into the control volume and then mass exit of the control volume. And because exergy is an extensive property, right? So it depends on the extent of the uh, working substance in a system, right? So that was also the case with entropy. So this, because this is a extensive property, in that case, this particular these two particular terms have been introduced into this exergy rate balance, right? So this is about mm, exergy rate balance, right? Okay, right. And then for steady state, right? For steady state, this will be zero, right? There will be no entropy uh, change in entropy with respect to time, right? Yeah, change in exergy, sorry, with respect to time in a steady state, right? Right. Okay. Then the next topic is second law efficiency, which is also exergetic efficiency, right? So exergetic efficiency. I'll just write the formula for it. So this is denoted by epsilon. I'll just briefly discuss what all these terms are, right? All right. So, so this has been discussed in terms of a system, right? Where the system is receiving some heat uh, from some source, right? And then it is operating at some heat, right? And this whole system is giving us some work, right? And then there is one more element linked to it, that is some heat that we are getting from the source in the system is being dissipated, right? So then there is some dissipation, right? So this that dissipation is uh, taken into consideration using this eta, right? And then there's the rest of this term for this exergetic efficiency, right? Where Ts is corresponding to the source, and this one is for the place where we are using the temperature at which we are utilizing our system to get some work, right? So this way, exergetic efficiency has been defined, right? So diagram has been given in the your lectures, lecture notes, right? So you can just check that. I won't draw it here at present, right? It will unnecessarily take some more time, right? So then moving on to the last topic of last lecture of this week, right? Of lecture 9 is energy versus exergy. So here, what has been discussed is how exergy is different from energy. So, initially, when I discussed exergy, I told you that though energy is conserved, but exergy is not conserved, right? But then there are few commonalities between these two. Like energy is also extensive property, right? And then exergy is also extensive property. Okay. So such comparison has been done between these two terms in this particular. Okay. So this is about the topics that have been covered in this particular week's lectures. Right? So next we will move on to questions based on concepts that we have studied, or the theoretical questions. Right? Okay. And after that, we will discuss the numerical questions. Right? So let's discuss this. Okay. And at 4 p.m. we'll take a short break of 5 minutes. Right? Okay. So conceptual questions I have kept pretty straightforward, right? So if you have gone through the notes of your lectures, you'll be able to answer these questions, right? So, so first question is on turbines, right? This is from lecture 7, and it states that in turbines, change in enthalpy during expansion is greater in actual than in isentropic conditions. So, well, this will be a true statement or false statement. We can try to answer this question, and then we can, and I can discuss this question.
False.
False. Okay. So Prakash says it's a false statement. Right. So though I will ask questions from you, but then it's also important that I discuss the question, right? So so the statement says that in turbines change in enthalpy during expansion. So the statement first talks about turbine, right? First, and then it talks about change in enthalpy, right? And then it says expansion. So is it true that expansion takes place in turbines? So yes, that is also true, right? So change. So it talks about change in enthalpy. Then it says it's greater, right? In actual, than in isentropic condition. So in actual, the change in enthalpy for expansion will be greater. It says that. So whether this statement is true or false. So I'll just refer to the diagram I have drawn. So if you see here, so we have moved from state 1 to state 2, right? During the expansion in some turbine. So, and the state 2s is the isentropic state, right? So had the situations been isentropic, this is for that, right? So in the first case, the enthalpy change is H1 minus H2, and in the isentropic case, it is H1 minus H2. So this is the actual one, right? And this is the isentropic one. So clearly from the diagram, we can see that for the actual one, it is lesser, right? And for the isentropic one, it is greater. So, but the statement given to us is telling something opposite, right? So in that case, it will be a false statement. Okay. So now we will move on to next question. So this question is on compressors. Again, same type of question. In compressors, change in enthalpy during compression is greater in actual than in isentropic conditions. So what is the case with the compressors? So we just discussed the turbines, the case for turbines, and now the question is on compressors. So the question here talks about compressors, then it talks about change in enthalpy. Then it says compression is taking place, right? And this enthalpy change is greater in actual than in isentropic conditions. So whether this statement is true or false. So it's better we again refer to the diagram, right? So if you remember the diagram, in that case, it becomes easy to handle uh, such questions, right? So this is for a compressor, right? This diagram is for compressor. So here we are moving from again from state 1 to state 2, right? Here enthalpy is increasing for state 2, right? Yes. And then for isentropic condition, there is no change in the in the entropy. But then for the actual uh, state, right? For the actual compression, there is increase in entropy also, right? So, so the change in enthalpy in case of isentropic process, compression, will be less, and the change in enthalpy for actual compression will be higher, right? So, so the statement says that for the actual it will be greater, right? So this comes out to be a true statement, right? So this statement is correct. Right? Okay. So this is about turbines and compressors. Moving on to next question. So this question is on nozzles and diffusers. Whether this statement is correct or not. Please try to answer this. Okay, so this is a straightforward question, right? Nozzles are basically used to accelerate the flow, and diffusers are as the name also suggests diffuse. Right? So diffuser is to decelerate the flow rate. So in power plants also we use nozzles and diffusers, and then in aircrafts also we use nozzles and diffusers with engines. Right. So this statement is a false statement. Straightforward question. Nothing much to do in this question. Okay. So we'll move on to the next question. Yes. Whether this statement is correct or not. So again, question asks about actual, right? And then it says specific kinetic energy for what? For which device? For nozzle, right? And then for nozzle at exit, and then it is doing some comparison that it is greater than this and it is greater than that, and the comparison is between two cases, right? One is the actual case and then one is the isentropic case. Okay, so this is same as was for turbines and compressors where we were comparing the actual and isentropic cases, right? So this question is based on basically the efficiency, isentropic efficiency of nozzles. Okay? So there the efficiency is written, so I have written it already. So here if you see, so the V2 is this velocity at the exit for a nozzle, and then in the numerator the V2 is for actual case, and in the denominator the V2 is for isentropic case. Okay, so the efficiency of nozzles, if you refer to this Moran and Shapiro, right, book, you will find there that this, if I remember it correctly, this remains around 95%. This efficiency remains around 95%. That is, this is less than one, right? In that case, the numerator will be lesser than the denominator, right? So, which essentially means that the exit velocity for isentropic case will be higher, right? And now if we see our question, the question says that it is greater for the actual case than for isentropic case, which is not correct. Right? So this comes out as a false statement. Okay. Then moving on to next question. Okay. So this question is based on the discussion we have done in session 1, review of basic thermodynamics, where we saw the sign conventions for work and heat, right? So if we remember that discussion, we will be able to answer this question. So this is question number 5, and it states that work transfer in case of compressors and pumps is always. So whether it is positive or negative. Please try to answer this.
Negative.
Negative. So Pika says negative. So we have learned in session 1 or week 1 that when work is done on the system, in that case it is negative. When work is done by the system in that case, the sign convention says that it is positive. And opposite is the case with heat. Yes. So when heat is added in the system, in that case, we consider it as positive, and when heat is ejected out of the system, in that case, it is negative. So in that case, because in compressors we compress some gas or liquid, right? So work is done in that case, and work transfer is then negative. Then moving on to the next question, which is question number 6. So the question again is on compressors and pumps. So we have 4 options. You can try to answer this.
Option B. Smaller, larger.
Smaller, larger. Okay. This is what Prakash says. Okay. So the question says that this is question number 6, right? So for same pressure rise, the pump requires much dash work input per unit mass flowing. Then in compressor, right? So pump is basically where liquids are involved, and compressor is used where gases are involved, right? Or compressible uh, substances involved. So firstly, it says that pump requires, so whether pump requires uh, work, right, per unit mass flowing greater or lesser than the compressor. First, we have to answer this, and then we have to answer that what is the cause for that, right? Okay, so if you see your lecture 7, right? Discussion on compressors and pumps in lecture 7. So there you will find that the work requirement for pump is smaller, right? In case of compressor. And the reason for that is specific volume. And what is specific volume? Specific volume is basically inverse of density. Yes. Am I right? Specific volume basically is 1 by rho, right? So in that case, because the density of liquids is higher, right? So in that case, specific volume will be smaller for liquids, right? So this is directly smaller from the knowledge of whether liquids are dense or gases are dense, right? And then if we see the work requirement, right? So the discussion on compressors and pumps states that the work requirement in case of pumps is smaller, right? So if we have to compress a gas, it will take more work in comparison to liquids, right? So in that case, option A is correct, right? So first, this fill in the blank was correctly answered, but then for the second, it was straightforward based on whether the specific volume for liquid is higher in comparison to gases or not, right? Okay. So yes, though exergy is a property, but then there are some peculiarities related to exergy that we must keep in our mind when we are studying exergy. So this is one such statement. So is exergy a conserved property or not? You can try to answer this. We know energy is a conserved property, right? From law of conservation of energy. We know mass is a conserved property, law of conservation of mass, right? And then we also know that momentum also remains conserved, right? So whether exergy remains conserved or not. So I have discussed it. Okay. You see the exergy balance, right? For both a closed system and for a controlled volume. In that case, you will see the exergy is being destructed, right? Exergy destruction is there because of irreversibilities in the system, right? The irreversibilities which lead to entropy production and then also exergy destruction, which is here T naught or into sigma, and here is E with subscript D, right? So because exergy is being destructed in a system, in that case, we cannot say that exergy is remaining conserved, right? So this becomes a false statement. This is B option. So it's already 4 p.m., right? It's 2 minutes past 4 p.m. So we shall take a 5 minutes break, quick break, and then after the break, we shall complete the remaining part of the session. Thank you. Okay, so we can continue with the remaining session, right? So then the next question is on concept of exergy, right? So this is from lecture 8, I believe. And the question states that at equilibrium, the body and atmosphere possess same energy and there is no further work potential for the body. Okay, so this is the basically the statement uh, of exergy, right? So when a system attains dead state, right, comes in equilibrium with the dead state, in that case, it has no further potential to do any work, right? And this is what the statement is also saying here, right? So at equilibrium, the body and atmosphere possess. So by body we mean system, right? And then by atmosphere we mean environment. So there is no further work potential for the body. This is the correct statement. So this is correct statement. Okay. Option A. So moving on to next question. So this question again is on concept of exergy from lecture 8. So exergy is interpreted as maximum theoretical value of work from a system. So again, this is the uh, definition of exergy, right? So this is the maximum theoretical value of work from a system. So if we have to get the mathematical expression for this exergy, so what we basically do is we solve for the work, right, using the energy balance equations, and from there we get our this theoretical maximum theoretical exergy value. Okay. So which I have also written here, right? Exergy for a system, which includes the internal energy, right? The pressure energy, right? And then in terms of entropy, terms are there, and then there is kinetic and potential energy. So all this comprises, or all this is considered in the exergy's definition. Right, so this is a true statement, straightforward. Moving on to next question. Exergy is an intensive thermodynamic property. So we can try to answer this. Okay, so the statement says exergy, then it's an intensive thermodynamic property. So intensive thermodynamic property, as we know, is that property which does not depend on the extent of that property. For example, pressure. Pressure is an extensive property, right? And temperature is an sorry, pressure is an intensive property, right? It doesn't depend on the extent of the subject for which we are defining the pressure, and then temperature. It doesn't depend on the extent, right, of the subject for which we are defining the temperature, right? But then whether exergy is an intrinsic property or not. If you see, or if we see the expression for exergy, right? So it has energy terms, basically, right? The exergy basically is work, maximum theoretical work, and it has energy terms, right? And then entropy also, entropy terms also. But then all these terms that are there in the exergy's expression, all these are extensive properties, right? They depend on the extent, right? Entropy also depends on the extent, right? So entropy is also extensive property, right? So in that way, this becomes a false statement, right? Because exergy is an extensive thermodynamic property. So this becomes a false statement. Okay. So we have next question on our screens. The question is on concept of exergy. So this is from the aspects, 5 aspects of exergy we have discussed in lecture 8. So exergy, the statement says that exergy cannot be negative. So whether this is a true statement or false statement. You can try to answer this. Okay. So exergy basically is the potential of a system, right? And potential of the system to do work, right? And this potential is explained with reference to a state, particular state that we name as dead state, right? And when our system reaches this dead state, in that case, it loses all its potential or exergy or maximum theoretical work, right? And that is its lowest ebb, right? Beyond that, it doesn't go, right? So when the statement says that exergy cannot be negative, so this is a true statement. Okay. So exergy is always defined as a positive property, right? But whether this is also the case for Exergy change or not, that we shall see in the later questions. But for the time being, whether Exergy can be negative, no, Exergy cannot be negative. Okay, sorry, this is a true statement. Right? Okay. So let's move on to the next question. That is question number 12. This question again is on concept of exergy from lecture number 8. And it states that when a system is at dead state, the value of exergy is finite. So whether the statement is true or false. Okay, so we have a system, and then the statement talks about dead state, then it talks about exergy, and then whether it is finite or not. So when the system reaches dead state, right, which is the state in which the environment is, in that case, it loses all its potential to do work, right? All its potential in terms of work that can be extracted from that particular system. In that case, because the potential is not available, in that case, the exergy in numerical term will also not be there. Right? So if the question says that exergy is finite, in that case it becomes a false statement. Exergy in that case will be zero. So when the system has attained its dead state, in that case exergy is zero. Correct? And because the statement says that it is finite, in that case we will answer it as a false statement, which is also the case. Moving on to next question. The question again is from concept of Exergy, and this is question number 13, and it states that maximum theoretical work is possible when there are no irreversibilities in the system. Yes, so whether this statement is true or false, we can try to answer this. So we can answer this question if we know what is the impact of irreversibilities on the system. So what does an irreversibility do? First, we need to know this, right? So irreversibility leads to destruction in Exergy. In the entropy discussion, it was entropy production, which was the result of irreversibilities. And here it has come as Exergy destruction. So irreversibility is leading to Exergy destruction, right? That is, it is destructing some potential of our system. So it is reducing some chunk from the maximum theoretical work that is possible in a system by a system. So when there will be no irreversibility, then this destruction term will be absent from our exergy expression. And in that case, it will be possible to have maximum theoretical work in the system. So when the statement says that it is possible when there are no irreversibilities in the system, that is system is internally reversible. In that case, the statement is a true statement. Right? Okay, so we will move on to next question. So there are still few Theoretical questions, conceptual questions, sorry. Left. Okay, so next question is on exergy of a system. So this is fill in the blank type of question. And it states that question number 14, exergy dash as the state of system moves away from its dead state. So if a system in terms of its state, current state, is moving away from the dead state, in that case, what can we tell about the exergy of that system? First option is increases, second option is decreases, third option is remains constant, last option is we cannot say, we cannot comment on this directly. So maybe there are some other factors involved which needs to be which need to be considered when we are answering this question. So this is a fundamental question. So if the state of the system is moving towards the dead state, in that case, it is losing its exergy. If it is moving, the state is moving away from the dead state, in that case, exergy is increasing, right? And from the options available, option A says that it increases. So in that case, option A is the correct answer. Okay. So moving on to next question. This question is on closed system exergy balance. And this is question number 15. And it states that the change in exergy of the system is associated with. So when we are dealing with the change in exergy of a system, then what do we consider? So when a system moves from one state to another state, in that scenario, the change that the system takes place, the change that takes place in the system, that is because of what? So if we see the options say it is because of exergy transfer only. Next option says that it is because of exergy destruction only. Next option says that it is because of both Exergy transfer and Exergy destruction. And the last of these is none of the above. That is the correct answer. Correct fill in the blank has not been provided in the options. Okay, so if you remember this, the closed system Exergy balance. Exergy change is because of Exergy transfer across the system boundaries and Exergy destruction because of irreversibilities, right? So out of the given options, option C correctly answers the question. In that case, C is the correct option. Moving on to next question. Again, the question is on closed system Exergy balance. It talks about Exergy destruction, and then it says that it can be negative. So if we see Exergy destruction, it is because of irreversibilities, and the mathematical expression for it has entropy production in it, right? So it is basically T naught into sigma, right? And in session 2, we have seen that entropy production can never be negative. Entropy production is always positive. If there is a reversal, if the system is reversible, internally reversible, in that case there will be zero entropy production, and if there are irreversibilities, in that case there will be some finite entropy production. And Exergy destruction is derived from entropy production only. So when the statement says that the value of Exergy destruction can be negative, so that cannot be possible and is a false statement. Correct? So moving on to next question. So this question is on closed system Exergy balance. Again, the question is on the topic closed system Exergy balance. And it is a fill in the blank type of question. Question number 17, it states that the only processes of an isolated system that occur are those for which Exergy So if you see this, right, for a closed system. So this is question number 17. So Exergy change here is so this is our Exergy change. So E subscript Q is for heat transfer, that is leading to Exergy transfer. E subscript W is for work transfer, right? That is leading to Exergy transfer. And E subscript D is for Exergy destruction. And the question here says that it's an isolated system. Because it's an isolated system, in that case, EQ will be equal to EW will be equal to 0, right? And in that case, what we are left with is E2 minus E1 is equal to minus ED, right? So only Exergy destruction term is there in the picture. So when the statement says that only processes of an isolated system that occur are those for which Exergy dash. So for isolated system, if you see, because E subscript D will always be positive, in that case the change is negative, right? So if the Exergy change is negative, sorry, is negative, in that case the process will be possible, right? So B option is correct. Okay. So then two more questions. After that, we will do numerical questions. So exergetic efficiency is always less than unity, whether this is a true statement or false statement. So this is a factual, more of a factual question, right? So if you see the exergetic efficiency, right? E- Even if the eta is 100% efficient, right? There is, let's say, there is no heat ejection out of the system, right? Or heat dissipation or heat loss. Even in that case, also the reference says that it remains less than one, right? So this is a true statement. Okay, moving on to next question. So when the flow moves from input to inlet to exit of a turbine, in that case, what happens to the exergy of the flow? This is what the question asks. Because we know that in turbines, we extract work from a turbine, right? That is what is the work of a turbine. So in that case, it loses its potential at as it reaches the exit of the turbine. Right? So in that case, what will be the answer to this? What will be the answer to this question? Because the potential decreases, in that case, the exergy also decreases. Okay, so moving on to numerical questions. We're still left with 15 minutes. So question number 20 to 23. So this is about a steam and a nozzle and a divergent nozzle, right? Well insulated. This nozzle is well insulated, right? And then some conditions are given, right? At inlet conditions are given, pressure conditions are given, temperature conditions are given, and it leaves as a saturated vapor. And the environment of this nozzle has a temperature of 273 Kelvin, right? Further, the steam inlet and exit velocities are 527 and 46, right? So V1 is 527, V2 is 46. Exit area also is given, right? 0.8534 exit area is given. Then some additional information is also given. So for inlet, some conditions are given, like enthalpy is given, and then entropy is given. And same is for outlet, enthalpy is given, entropy is given, and then specific volume is also given for the outlet. Okay, so all these points have been given to us, right? And now we shall see how we solve these four problems. So first is, so this is from Exergy rate balance for close for control volume, right? So this is from that topic because we are witnessing a flow, right, across a nozzle, which is a divergent nozzle. Okay. So first it says that steam flow rate we need to find, right, in kg per second. That is mass flow rate we need to find, right? So what is mass flow rate? Question number 20. Is rho AV, right? Rho can also be written as in terms of specific volume. AV by nu, right? And for our case, at the exit area is given. Velocity at the exit is also given. And then the specific volume is also given, right? If you see, specific volume is given here. This, right? Okay. Now, so if you try to solve this, 0.0534 into 46. Exit velocity is for 46. This. If we calculate this, what will we get? Please solve this. Okay, so this is about question number 22, right? So here first I wrote the Exergy balance expression, right? And then from here we'll find the entropy equal to balance, and then from here we will find out the entropy generation, right, or production that we have discussed it in terms of entropy production in the lectures, right? So the expression we have here is this, right? So by mistake my microphone was off for question number 21, I believe. So in question 21, uh, we solved it using the energy balance, right? And from there we found out the heat loss. And then in that I said that we have solved it in terms of kilojoule terms only, right? And because we solved it in terms of kilojoules, so I have not changed the velocity terms. Uh, I have not changed the enthalpy terms by multiplying it with 1000. And in that case, what I have done is for the velocity terms, I have multiplied it with 1 by 1000. In that case, the answer I'll get will be in kilowatt terms, right? So this we have done. And then for question number 22, we are finding out the entropy production, right? Okay. And then if we try to work this out, this comes out to be minus 6.3061 plus 6.3494, right? And if we work this out, this comes out to be 0.0433, right? Okay. So this is about question number 22. So it's already 5. So last question. Now the last question is, so this is 0.0433. Calculate the rate of Exergy dissipation. So the rate of Exergy dissipation, so I have in the conceptual questions repeatedly I have been discussing this point that Exergy destruction or dissipation is coming from entropy production, right? So when we have to solve for Exergy dissipation or destruction, in that case it will be just multiplied with the entropy production term, right? And this comes out to be this kilowatt, right? So this was our last question, right? So we have come to the end of this session, live tutorial session number 3, right? So I'll conclude this session. So we started with the topics that have been discussed in week 3 of advanced thermodynamics and combustion, that is this course. And the topics were on exergy and exergy balance for closed system and for control volume, right? And from there we moved on to conceptual questions. We discussed 19 conceptual questions based on isentropic efficiencies for turbines, nozzles, compressors. Then we did discussion on questions based on Exergy balance for closed system, and then in the uh, later parts of the this conceptual questions section, we did discussion on Exergy balance for control volume, right? Questions based on that, and after that we moved on to numerical questions section, and there we solved 4 questions based on Exergy balance for control volume, right? And this way we just completed our session, right? And so uh, now we shall end this session here only, and thank you for joining the session, right? And the next session will again be on the coming Sunday at same timing from 3 to 5 p.m. And till then, goodbye and happy learning. Thank you.